Alright, I'm Tommy Yu, Cosmos 2014 UC Davis, cluster 3, and I'm going to start out with the two guys, Pierre Simon Laplace and Claude Louis Navier. Pictures. Alright, so what is Laplace? Well, it's a city in Louisiana, you can see right here. It's also the most successful restaurant chain in the Netherlands. And see here, I'm not, this is a hook, by the way. So who am I going to talk about? I'm going to talk about the French mathematician and astronomer Laplace. You can see, born March 23rd, 1749, died March 5th, 1827, and he's considered by some as a Newton of France. Okay, so what did Laplace do exactly? He formulated Laplace's equation, which is a second-order partial differential equation. It's right here. And he also pioneered the Laplace transform. More work. So he was a pioneer in mathematical physics. He developed the nebular hypothesis of the origin of the solar system, and he was one of the first to propose the existence of black holes. Alright, so the Traité de Mécanique Céleste was his 5-volume textbook. It means the celestial mechanics, and they talked about the mathematical understanding of the motion of heavenly bodies. The book's right here. So he also had large contributions to statistics. He wrote several texts, and he developed the least squares method for assessing observational data, and he's considered the father of the field of probability. Alright, so the Laplace transform. It was one of his biggest mathematical contributions. It's a widely used integral transform. It has applications in physics and engineering. It's useful in solving, more on it. This is a table of the most common Laplace transformations. I don't know what. He developed it during his work on probability theory. So more work. He developed a method for estimating integrals. He also discussed the general theory of determinants, and he claimed that even degree equations must have at least one real quadratic factor. Even more work. He developed a theory of capillary action. It's right there. He helped develop the Young-Laplace equation, and he was the first to point out that the speed of sound in air depends on the heat concentration. So, summary of Laplace. He was a French mathematician and astronomer, pivotal to the development of astronomy and statistics, formulated Laplace equation and the Laplace transform, and he's considered the Newton of France. So right here we have second guy, Navier, French engineer, physicist. You can see when he was born and when he died. He specialized in mechanics. There's a picture. Alright, so Navier's work. His main contribution were the Navier-Stokes equations. He was a specialist in road and bridge building, where he developed his theory of suspension bridges. Well, the Navier-Stokes equations describe the motion of fluid substances. He developed them without fully understanding the physics of what he was doing, and they arose by applying Newton's second law to fluid motion. So why are these equations important? Well, they can be used to describe the physics of everyday events, such as weather, ocean currents, water flow in pipes, and airflow around the wing. The airflow right here, and ocean currents right here. So this table to the right is a three-dimensional unsteady form of the Navier-Stokes equations, and they describe the relationship between velocity, pressure, temperature, and density. Other contributions. He formulated the general theory of elasticity in mathematically usable form. He made it usable in the field of construction for the first time with sufficient accuracy. More contributions. In 1819, he determined the zero line of mechanical stress, which corrected one of Galileo's incorrect results. In 1826, he developed the elastic modulus, the property of material independent of the second moment of area. So, summary of him: French engineer, physicist, developed the very important Navier-Stokes equations, and He's considered the founder of modern structural analysis. And to the people. Alright, so my topic was actuators. Again, it's my name. This right here is an example of an actuator, so let's wait for this to get started. Alright, so what exactly is an actuator? Well, it's a motor that actuates or controls a mechanism or system. It converts some type of motion, some type of energy into some type of motion. And so right here we have an assortment of actuators, several different types here, and the picture to the right just shows a bunch of pictures of linear actuators. So the history of actuators, they can be traced back to Archimedes and his screw, which he used to haul water from boats, as a linear actuator, and then there were also mechanisms that crushed grapes into wine. Okay, so actuators can be categorized in four different ways. Right now I'm going to talk about energy. So the four main types are hydraulic, pneumatic, electrical, and mechanical. So hydraulic actuators. These actuators give a unidirectional force through a unidirectional stroke. They're used in construction equipment, manufacturing machinery, and civil engineering. This right here is a diagram. So these types of actuators generate more energy than other types because liquid cannot be compressed. They convert fluid pressure into motion, and they typically use oil as the hydraulic fluid. And so next we have pneumatic actuators. These types of actuators convert energy in the form of compressed air into mechanical motion, which can be rotary or linear, and pneumatic. Alright, more. Pneumatic actuators are the most common type of actuators. They're almost always made of metal, and they're used in air compressors, grippers, pumps, and switches. And some pictures right here. And so these are examples. This is our robot, this is another robot, and right here. And here we used pneumatic pistons to control the arm that picked up the ball. And that's another pneumatic actuator. Next we have electrical actuators. These are controlled using an alternating current and a motor. They're quiet, non-toxic, and efficient, mainly because they do not use oil, unlike electrical actuators control equipment like multi-turn valves, and they're also used in assembly, packaging and testing, and magnetic solenoids, and this right here is a valve. Next we have mechanical actuators. They normally operate by conversion of rotary motion into linear motion, and so different types of conversion include a screw, wheel, and axle and cam, and this right here is a screw. So some mechanical actuators only pull, and some only push. And applications include lasers, optics, positioning of linear stages, rotary stages, or mirror mounts. And so, summary of energy category. Four main types: hydraulic, pneumatic, mechanical, electrical. Each has its own advantages and disadvantages, and they have their own unique uses. So actuators can also be categorized by motion. There are four main types again: multi-turn, quarter-turn, linear, and lever. I'm going to go into depth with linear actuators, which are the most common. Okay, so linear actuators, they create motion in a straight line. That's why they're called linear actuators. They're used in machine tools, and they're also used in computer peripherals such as disk drives and printers. And that's a picture of a linear actuator. So when you're measuring performance of an actuator, you normally measure it by these four main performance metrics: force, speed, operating conditions, and durability. So, summary of actuators. Actuators are very important in our lives. You may not always see them, but they're there. And there are many different types of actuators that come in different shapes and sizes. And so, yeah, thanks.